All right. So the first question was the level of organization within the body. I think most people got that right. That was chemical to cellular to tissue to organs, organ system, organism. Okay? It's the foundation of everything that we talk about, because the way that this class is organized is through these levels of organization. We're starting at the chemical level and we're moving our way up. So underline that was actually. Okay. When a sensor detects a change, it will send a signal to the brain, which is also the integrating center, via an afferent pathway. Remember, we talked about that. You have a variable, and it has to be sensed by a receptor. And then once the receptor senses the signal, sends it to the brain via an afferent pathway, okay, to the integrating center. Then the integrating center compares it to the set point, and then we make the change via an efferent pathway to the effector organ, whatever the organ might be, okay? It's the maximum number of electrons that the second orbital in an element can have was 8 electrons. So here, let's highlight this. 8 electrons. In body membranes, the layer of tissue that's in direct interaction with the organ itself was the visceral layer. The outer portion was called what? The parietal layer. Now, why was that, and what was in between? Serous fluid, or serraceous fluid. Why was that important to understand? Yes, how we're protecting the internal organs. Right, you remember I showed you that example. If I take my hand, which is skin, it's an organ, and I sit here and rub it across this table, for example, and with the heart 70 times per minute, my hand will get raw. I will damage my skin. This is constantly occurring within our internal organs. The heart is beating at least 70 times per minute and rubbing against stuff constantly. That's damaging. And so we have these body membranes with fluid in between. We have these 2 layers of fluid in between to prevent the friction and prevent the damage of our organs that are constantly moving. Okay? Positive feedback mechanisms. This was where the variable was moving in the same direction as the original stimulus. So in essence, if the variable has increased, it will move even more for increasing. It will move in the same direction. So this answer was false. The atomic number of an element is directly related to the number of which atom. And you remember the atoms, there was only 3. There's electrons, neutrons, and protons. Positrons in this case is not a thing. Okay? It was directly related to the number of protons. The number of protons that are in the nucleus. Now, I told you a lot of people like to say that the atomic number is directly related to the electrons. No, it's directly related to the protons, and the protons, since the elements have to be balanced, can tell you about the number of electrons. Okay? And one day you'll figure out why this is important to understand, possibly in this class. I don't know if we talk about it later on. But then there was this that's certainly very important to understand. This one, not so much. This is certainly very important to remember. There were 2 models that we talked about when we talked about elements. Okay? There was an orbital model and there was a planetary model. The planetary model is if I have this nucleus, I have all these plus charges and then neutrons, whatever, we're drawing the circles, and we have these orbitals around them, and we put the electrons around it like this. In these orbitals. This was the planetary model. And then I told you that there was something called an orbital model, where we had the nucleus, and instead of them being in these orbitals, the orbitals were waves of energy. Okay? So it was more like this. It was more like a cloud. And I told you that you can never, ever capture a single electron around an element. It's not possible. They're moving so fast that you can't capture one. So in reality, it's a wave. It's not a single atom that's sitting there like on the planetary model. It's a wave of energy. It's not these single Now this isn't the live video, it's on a PDF, but it wasn't this. This was a way to help you understand. And I keep harping this to you all. Artists make pictures to help us understand things. But in reality, this is what it's actually looking like. It's a wave of energy. They're not really individual particles because you can never capture one. And so, you remember the magnets that I told you about? If you take two positive sides of a magnet and push it together, and you feel that ball of magnetism, whatever, and you try to push against it, that's what this is. That's energy. And that's what these elements actually look like. So the most accurate representation of an element is the orbital model, not the planetary. So that answer was false. Okay, this was a simple question on negative feedback. If creatinine levels is high in concentration in the blood, the resulting response would be to move in the opposite direction. So, to decrease blood creatinine levels. One function of the integumentary system, I tried to pick one that we talked about a lot. One function was replenish nutrients in the blood. That was not the case. That was more of digestive system. Help in movement of bones, that was skeletal muscle system, but it was to help regulate body temperature. We talked about multiple ways that it can do this, and you all have to know these multiple ways. One of them is if you get too hot, sweat glands start to release sweat, and the water on your skin, whenever you're moving, air will push against the water and it'll cool you off. If you get too cold, we talked about the hair follicle having those muscles that will, we might talk about those muscles today in lab, but they contract and they make the hair follicle stick up. That contraction of muscle generates heat. Okay? So that's where you get goosebumps from. And then we talked about another one of regulating blood flow. Right? So if your body temperature gets too high, then the skin will start pushing blood to the surface of it so that we can let off heat that's coming from the blood. And if you're too cold, then it starts keeping blood within your internal organs and keeping it away from the surface of the skin so you don't lose heat. Okay? So regulation of body temperature. Homeostasis is primarily maintained by negative feedback mechanisms. Okay? We talked about feedback mechanisms. We said there were two types. There's negative feedback, and we've had multiple questions on them already. Negative feedback, we're moving in the opposite direction. Positive feedback, we move in the same direction. But the most important thing I told you about positive feedback was that it does not maintain homeostasis. Okay? This does not maintain homeostasis. All homeostasis is being maintained by negative feedback. Okay? The two examples that I gave you, childbirth with contraction using oxytocin as a hormone to cause uterine contraction, that's not maintain homeostasis. That's not normal. You will not constantly be going through that throughout your life to survive. That is not a normal process, but that was an example of positive feedback. The same for blood clotting. You don't want to have blood clotting constantly occurring, or you increase the amount of clots and then you start breaking. No, that's not how that occurs. Because if you increase blood clots, But say, for example, it is a homeostatic mechanism. And so you increase blood clots, you increase the production of blood clots, and then you start decreasing them in this cycle, like negative feedback is. What happens? Somebody has to know what happens when you form blood clots. Something bad can really happen. You can clog your arteries, you can develop a stroke. So blood clotting was an example of positive feedback. However, it's not maintaining homeostasis. This is to solve a problem. You cut a blood vessel. Okay? That's not maintaining homeostasis. Okay, in feedback mechanism, again, here's another feedback mechanism question. The component that's defined as the factor being regulated is the variable. Now, I've already walked through that with you all. And then we talked about these isotopes. Okay, this is actually a question. So the rest of these questions look similar to my exam questions. This is probably considered a more trickier one that would be on my exams. And this one was on one from a class that I taught in the spring, was that a radioisotope is defined as, and we mentioned isotopes. We said isotopes were the element that had different number of neutrons. That was it. We didn't say protons, we didn't say electrons. Different number of neutrons. However, we talked about this subcategory of isotopes called radioisotopes. And so sometimes when you lose or gain neutrons, the element can become unstable. And then all of a sudden you start releasing protons, or you start releasing electrons or energy from those things. And then that causes radiation. We talked about alpha, beta, and gamma radiation. That was the definition of an isotope. An element with different number of neutrons that becomes unstable and releases charged particles. Okay. So I'll save that. I probably won't post it. I might make a quiz on Blackboard, just like a practice quiz, because you all have an exam tomorrow, and just put it on there, and you all can practice this quiz again, just as like a study tool. Okay. Does anybody have any questions from the quiz? Make sure you count your points and like which ones I counted right and wrong. Sometimes when I'm going fast, I can make mistakes. Okay. So, we really finished talking about ionic bonds, and we started on covalent bonds. And we talked about single, double, and triple bonds. That's obviously important for the exam. And we started talking about the different types of covalent bonds. Okay, and remember, this is the lecture 2, part 3, I think is what it is on Blackboard. Lecture 2, part 2 is kind of like overlap between 1 and 3, so I just started with part 3. So we talked about ionic bonds, and we said that these were attractions between charges or between opposite charge elements. Okay, it's very simple to understand. It's the moderately strong type of bond. We talked about this. This is totally not pertinent to the exam. This is not at all. Not even focus on it. And we talked about covalent bonds. And we said this was a sharing between electrons. And this was different than ionic because ionic was more of a transfer. We're like totally transferring electrons, although we still have the bond. But covalent bonds were sharing. And then there were 2 types. We said that there were polar covalent bonds and there were non-polar covalent bonds. Non-polar was where the electrons are being shared equally between the 2 elements. Okay? And so usually this is between elements of the same kind. oxygen and oxygen, or fluorine and fluorine, or hydrogen and hydrogen. Okay? Usually this is between the same elements. This is one electron, this is the other electron, and understand this as a wave. They're constantly moving between the two. Then we talked about polar covalent bonds. And this was unequal sharing. And I brought up this idea of electronegativity. Okay? Electronegativity was how attracted an element is to electrons. How bad does it want an electron? Okay? This is what's called electronegativity. And there's a way to read this on the periodic table, which was usually is the lowest here at the bottom left corner of the periodic table, and electronegativity increases as you move up and to the right. And so inherently fluorine was the most electronegative element. Now question, why aren't these electronegative? Okay, they're noble gases, but it's not that they're unstable, they're very stable. Because they have their orbitals already filled. Right? I said that the octet rule was where you always want your outer shell completely filled. And if it's not filled, then you are unstable. Okay? And so this is where understanding how many electrons that an orbital has becomes important. Because the first orbital holds how many electrons? 2. Who said that? Okay, 2 electrons. The second one holds how many? 8. 8 electrons. So if I write helium on the board, how many electrons is that? 2. So I'll fill up this shell. The outer shell is filled. I don't want to give any electrons, and I don't want to take any. It's stable. What was the next one? Neon. Neon has 10. So this first layer has 2. The second layer has 8. It's completely filled. It's not going to want to give any electrons, and it doesn't want to take any. It's stable. It is totally unreactive. So the most reactive element, or the most electronegative element, is fluorine. Okay? Now, this is how we determine if a bond is polar or not. And I'll explain why. If I had an element, we'll say sodium, or let's do sodium has 11, 2. Okay, we'll say sodium. We're talking about sodium. Sodium has 11 electrons. So the first orbital is going to have 2 electrons. Second one's completely filled with 8. 1, 2, 3, 4, 5, 6, 7, 8. And then the next one has 1. Now the third orbital needs 18 electrons to be stable, right? This is its valence shell, the outermost shell. The goal of the game is to try to keep the outermost shell filled. And we'll say let's say fluorine. Yeah, we'll say fluorine. 1, 2, 3, 4, 5, 6, 7. Right, so we're at 7 in this outermost shell. Okay. How many electrons does this need to be stable? 1. I need 1 electron to be stable. Everything wants to be stable. Like I explained to you, the chair example. Okay? You might be anxious, you might be stressed. Your goal is to try to decrease that anxiousness and decrease that stress. That's instability. Now, if you're laying down on the couch watching a movie, you are incredibly stable. You don't want to do anything. That's the noble gases. Well, all of these elements want to get to that point, and they'll find any way to get there. How many electrons does this need to be stable? 17. Now, let me ask you this. What's the easiest way for this element to become stable? If you lose one. Because if I lose one, now I've filled out this outer shell. Now I'm stable. So if I lose that electron, I become stable. Now the easiest way for this one to become stable, fluorine for example, is to gain one. Just one. It wouldn't be to lose all 7, would it? That wouldn't make any sense. The easiest way for it to become stable is 7, or 1. That's the easiest way for it to become stable. So, that explains why this is incredibly electronegative. Because it only needs 1 to become stable. So it wants one a lot worse than this one does. Okay, this is essentially the path of least resistance. Okay, this is the path to take that has the least resistance. Would be for this element to lose 1 and this one to gain 1. Meaning that this element wants electrons more than the rest, which is the definition of electronegativity. I want electrons more than something else. And in that case, fluorine is the most electronegative element. Okay? Sodium's not so much, right? It's to the right of the periodic table, and you see why already. It has only 1 electron in its orbital. So that creates a perfect way to form a bond. The best way is to share them. And so this is where the covalent bond comes into play. So now I have 1 here, and I need 1 here. Let's form a bond. Now we're sharing 2 electrons. Now, this is where the polar comes into play. The electrons stay with the more electronegative element longer. You remember I told you that these are waves. And when you're forming a bond, instead of the wave going around the element, now I've shifted it to a single point, a bond. And the wave is now going on between here, instead of going on around here. Now with polar bonds, you see it's an unequal sharing. So what happens is that the electron stays away from sodium, and it stays closer to fluorine, which is just F. It stays closer with fluorine for longer. And I'm pretty sure I drew that picture, right, of how this thing works. The electron will move here, it will try to come there very fast, and it will try to leave very slow. Okay? So it will be staying with fluorine longer. I mentioned that yesterday. It stays with the more electronegative element longer. That's an unequal sharing of electrons. That's what we're talking about. And it's because one element wants the electrons more than the other one. That's the reason. And so the way to determine if something's polar or not, you just look at the electronegativities. It's very simple. If you look at maybe magnesium or something over here, you can fill up the orbital shell and you can determine, okay, this one has maybe 2 electrons in its valence. Maybe that one will want to lose it a lot more than something that has 6 or 7 electrons in its valence shell. Okay? So that's why these elements are more electronegative than these ones. And so on an exam, it will be very easy to determine whether something is a polar covalent bond or a non-polar covalent bond. Does that make sense to everybody? Okay. And so here's some definitions, like elements that have 6 or 7 electrons in the valence shell tend to be very electronegative. That's here and that's here. And then elements with 1 or 2, which are here and here in its valence shell, are less electronegative, or they are called electropositive. But typically you'll want to use this nomenclature, less electronegative. Okay. And these are the definitions that you'll certainly see this on an exam. One of these definitions. Now let's talk about this. This leads us to our third type of bond. So we've talked about ionic, we've talked about covalent, and we've talked about the 2 types of covalent bonds, polar and nonpolar. However, the polar covalent bond allows us to create another type of bond, and it's called the hydrogen bond. So say, for example, I have this very electronegative element, oxygen. Okay, we have 6 electrons in our valence shell, right? So I need 2. Hydrogen has how many electrons? 1. Has 1 electron. So it shares a bond with oxygen. It gives, you have 2 hydrogens that form a bond with oxygen. You've seen this compound multiple times in this class already. This is water. This is H2O. So a hydrogen is sharing its electrons with oxygen to fill oxygen's valence shell. Now, what type of bond is this? What type of bond will this be? A covalent bond with what type? Polar covalent bond. Because this is an unequal sharing. Hydrogen is way over there. Way over to the on this case it would be the left of the periodic table. And oxygen is way over there to the right. This is a very, very electronegative element. So the electrons are spending most of their time here in the rotation, in this bond. They're spending most of their time here. What charge are electrons? Electrons are negative. What happens is that when electrons spend most of their time with an element, you form what's called a partial charge. Okay? So you all can understand oxygen by itself is a neutral atom, has no charge. Well, all of a sudden you're adding 2 electrons that are spending most of their time here and a little bit of their time here. This starts to make oxygen partially negative. So now you have developed not a strong charge. It's not strong, but it's just a little bit negative. Because you understand that this electron's moving back and forth still. But it's spending most of their time here. Don't forget that this is a polar covalent bond. So now you're developing a partial negative charge. And this is the symbol for partial negative. Okay? I'm pretty sure this is a delta symbol. I have no clue. But you start forming a partial negative charge. Well, what happens here at hydrogen? It's sort of lost an electron, kind of. Not really, but the electron isn't spending a lot of time here. So the hydrogens develop this partial positive charge. Now understand, this is not a real charge. This is just a small positive charge that doesn't stay forever either. Right? Because the electrons will come back here. This is still an orbital. They'll still spend some time here. So it's not a real charge. Now, because of that, you can cause attractions between positives and negatives. And this is where the hydrogen bond comes from. Everybody knows what water is, right? There's a gallon of water right there. That's not just one H2O molecule. That's millions. And what happens is now you have all of these polar covalent bonds that are forming partial positives and partial negatives. They all have these partial charges to them. And all of a sudden, if I have these 2 molecules, these partial positives will attract to the partial negatives. So now I have 2 water molecules. They're sitting here. You can see that there's bonds between the hydrogens. These are polar covalent bonds. All of a sudden, boom, I've turned. The partial positive on this will attract the partial negative on the oxygen. Everybody understands that? Positives attracts to negatives. Sort of the concept of ionic bonds, but this is an attraction. This is not a bond form. Okay? We call it the hydrogen bond, but there's no sharing of electrons. You all see this. There's not a bond being formed. We are causing an attraction to where now all these millions of water molecules have now formed to face each other with partial positives and partial negatives because of the polar covalent bond, because of the partial charges that have formed on each one of these elements. So the key thing to get, and this will be a question on the exam, is that the hydrogen bond is not a bond. It's an attraction, it's a force. Just like two positives and negatives on a magnet coming together, but they're not completely touching. They're not sharing electrons. There's no bond that forms between the two. It's an attraction. Now, again, I'll harp on this. Why is this so important? Why do you think that this is so important? And I owe a lot of people cards, but why do you think that this is so important? While we're talking about what's called the hydrogen bond. Because there's an incredible amount of water. And so this is causing a lot of attractions in our body. These water will never exist as a single H2O molecule. So in essence, this is what's forming what we know within our body. All of these attractions that have now turned because of the polar covalent bond. So if I ask the question, can a hydrogen bond be formed on its own? The answer is no. Because you have to have the polar covalent bond because of the partial charges. And this is the symbol for the partial positive and negatives. Now, what I just described to you is also called a dipole or a dipole moment. This is where you're generating two partial charges on two different elements because of the polar covalent bond. It's called a dipole or a dipole moment. Okay? That's what's causing these partial charges to form. Now, you can see, and what the point that I'm trying to get across to you on this slide is that here's a covalent bond, or here's a polar covalent bond where we have two elements that are very different electronegativities. And that's what's causing the bond attraction. Here, like an example of carbon dioxide, you have a carbon and two oxygens that are similar electronegativities. They're very similar on the periodic table. So they're essentially equally sharing their electrons. And you should be able to identify whether something's polar or non-polar covalent just by looking at the periodic table and knowing the electronegativities, okay? Now, here are the strengths. Ionic bond somewhere in the ionic bond is in the middle strength. Do I have this strength even on here? Yeah, okay, they're here. So ionic bonds are sort of the intermediate, hydrogen bonds are the weakest, and covalent bonds are the strongest type of bond that you can have. However, you all know why hydrogen bonds are the weakest, right? Because they're not really bonds, they're attractions. Okay, there's no sharing of electrons. Now, hydrogen bonds are very important and they can become very strong because there's so many water molecules. And we'll talk more. You'll see, this is not the last time you'll see hydrogen bonds, okay? They're very important. Now, I don't want you to lose sight of what is going on with these bonds. This is still the two magnets coming together. This is still I guess I don't have it drawn anymore, but this is still that orbital of electrons. It's just moving between two elements. And so if you think about it, these bonds are the same attraction. There's just different reasons why they form. And that's why we have ionic, polar, covalent, and hydrogen. It's still the same attraction, just like the two magnets coming together. It's just a different reason why it's forming. And that's what you have to learn. Okay, no questions on that? Okay, cool. I didn't know I had this slide. Okay, you all can read this slide. This is everything that I've already said. But understand that this is a very weak force individually. Two water molecules, one hydrogen bond is very weak, but together it becomes a very strong force when you have something like this gallon of water or an entire cell. Now it begs the question, why do we learn this? I told you that there's water all over our body, but one of the most important examples is in our lungs. And water because that these bonds form together, there's this concept called surface tension. Okay? And the best way to explain surface tension is whenever the cohesion of the water molecules together forces things to move with it. So if I take water and I take it and pour it on this table, it will form something like this. They'll bubble up. The water will start as a big puddle, and then all of a sudden all these water molecules ball together. That's these attraction forces working in real time. They come together and they ball up. That's what's causing these bubbles here. Now, this certainly occurs whenever water interfaces with air. That's important to know. This concept of surface tension is very important though when we talk about the lungs. And one of the important things about the lungs is that we have water lining the inner lining of the lungs, all over it. One of the important things that our respiratory system does is that when we take in this dry air, we have to take it in and we have to add moisture to it. Otherwise, the dry air, just like happens on your skin, it will damage the inside of your lungs. Okay? Now, I just told you about this surface tension thing. The water will ball up. They'll ball up. This is surface tension is a force. When you get to the small portions of the lungs where we're interfacing with air and trying to exchange oxygen for CO2, these things are very tiny. Once we get to the lowest level, the portion that's interacting with those tiny blood vessels I told you that are touching every single cell, you can imagine that these things are very tiny. So what happens when you have water lining the inside of the lungs is that the surface tension will then take one side of this wall, this is a representation of right here, will take one side of this wall and the other side of this wall and fall up and pull the lung lining together. And it's very hard to pull apart. You would have to generate a lot of force inside your lungs to then pull these walls apart. Well, what happens when this thing collapses? You can't exchange gas anymore. That's a problem. So our lungs have these type of cells called type 2 pneumocytes. You don't have to know that, but they secrete a waxy substance, which is not on here, but it's called surfactant. And what surfactant is this is waxy substance. And this waxy substance will line the inside of the lungs. And just like if I took maybe a crayon and scrubbed it all over this table and poured water on there, it will allow the water to sort of flow all over the wax. It's a lot different than just this regular table. It reduces the surface tension of water. And so it allows our lungs to inflate. And now we can exchange gas with the blood. Well, this is very important, especially in babies, because sometimes premature babies don't develop these cells yet, these type 2 pneumocytes, and so they don't secrete that waxy substance. And so they develop something called respiratory distress syndrome, where now the water does not have this waxy substance to now smoothly, or reduce the surface tension and then smoothly come across the lung lining. Instead, they ball up because of the surface tension, because of these hydrogen bonds. And so they can't breathe. So babies can't breathe. So they have to be put on a special machine, a ventilator, that will increase the pressure and be able to pull these lung lining apart. Now, they have new drugs that can develop surfactant in the lungs, and you can put synthetic surfactant in the lungs. And so this is a very treatable thing now. However, it is a problem. Right? This is why that understanding the hydrogen bond is so important. Because of something like this. And of course, here's a representation of the hydrogen bond. It's usually shown in these lines instead of a full bond. Another important reason is because this is how we're holding DNA together. DNA is held together by hydrogen bonds. 2 strands of DNA in this double helix are held together by these double bonds. And attraction. Okay. So that's bonds. Anybody have any questions? certainly know what's going on with surface tension. We'll talk more about water today, actually. Now let's talk a little bit about energy. And really, in order to talk about energy, we have to talk about a concept called matter. Okay? And the definition of matter is anything that occupies space and has mass. It has to have mass, and it has to occupy space. If it occupies space and doesn't have mass, it's not matter. Okay, and there are examples of that. But so matter in our world is solids, liquids, and gases. On Earth, solids, liquids, and gases. Now, there's a concept called energy. Energy is the capacity to do work or put matter in motion. You cannot take matter and move it without energy. That's a very important concept to understand. And so, energy exists in two forms. There's something called potential energy, and hopefully this might be a little bit of a review for you all, but there's potential energy and there's kinetic energy. You have to know the difference between these two. But kinetic energy is actual movement of something. This is energy being used. Now, there's something called potential energy, which is energy that's there, but it's stored. It has not been used yet. And a great example is thinking of maybe like a hill and you have this big boulder. This is the common example that people give. Everybody understands that if this boulder is sitting on top of the hill, if it just gets a little bit of a push, then it will roll down this hill. Okay? All it needs is a little bit of energy to push it. Well, that energy that it takes to push the boulder is kinetic. Right? That's me physically doing it. The boulder sitting here has the potential to generate a lot of energy once it gets a little bit of a push and rolls down the hill, but it hasn't yet. And so it's holding the energy. This is what potential energy is. It's energy stored. Now, I told you a few days ago that energy is the movement of electrons. So, if, for example, you have two electrons here. If, for example, I break this bond, I have released electrons. Right? The movement of electrons is energy. So a perfect example of potential energy is the chemical bond. The chemical bond is holding the electrons there in place. And once you break a bond, the electrons go. Then it becomes kinetic energy. So chemical bond is probably a perfect example of potential energy. But one thing you have to understand, just like I said, you can't move an object without energy. Matter and energy are inseparable. Matter requires energy to do something. Now, there are multiple types of energy that I need you to know. There's chemical energy, what I just described. This is energy stored in the chemical bond. Potential energy. There's something called electrical energy. Is the movement of charged molecules, like electrons. This is something that you see in lights or whatever. Or like with the lights that we have above our head. This is electrical energy, the movement of electrons. Okay, then there's mechanical energy. This is energy directly involved in moving an object. Mechanical energy. Then there's something called radiant energy or electromagnetic radiation. This is energy that travels in waves. So charged particles that are traveling in waves. And we'll talk about that in a second, and it's right here. So there's this concept called the electromagnetic spectrum. And what I want you to understand is that this is a charged particle that's moving in waves. This is what I just called electromagnetic energy or radiation energy. Okay? Now, these particles can move in waves that are either further apart, these waves are further apart, or they can be closer together. That's called frequency. how close they are or far apart they are from each other. Now, as we get wider, the energy is less. There's less energy here than there is here. As they're closer together, it's very high energy. And as you can see, it's very toxic. We talked about gamma rays yesterday. Very toxic to the body. Now, as these charged particles get further apart, you develop what's called X-rays. Started with gamma rays, X-rays. Then you come to ultraviolet light, or ultraviolet waves. This is what's coming from sunlight. And then you have this small section of waves. This is still charged particles, okay? This is electromagnetic energy. You have this small section, so this is a very small range of frequency that develops what we call visual light. This can be detected by our eyes. The rest of these can't necessarily be, these cannot be detected by our eyes. There's a small section of frequency that can be detected by our eyes, and it's called the visible spectrum. It's very tight. This is this is nanometers. This is the distance between the waves, nanometers. And as you change the distance between those waves, it creates different colors. Right? We know this as the rainbow, but understand that there's many different colors that are sitting between based on single frequency changes. Okay? Now those same waves then elongate, so they have less energy. They become infrared waves, and then they become longer. They become microwaves, which we cannot detect. And then they become a little bit longer, which we have radio waves. Okay? So this is still on one spectrum. Simply the movement of charged particles in wave form. And there's a small section that we can detect, which is called the visible spectrum. Very small in this huge spectrum. Okay? That's what electromagnetic energy is. And again, here's another example. It's just showing you how small this wave that we can detect, this small frequency that we can detect across this whole thing. Okay. So we talked about energy, but the one thing I want to get across to you is energy can be converted from one to another. In essence, I can convert chemical energy to electrical energy. I just showed you that example. If I break the bond, electrons are released. That is transferring one type of energy to the next. Right? We can convert energy from one to the other. Other examples are chemical. Gasoline is a form of chemical energy. That chemical energy will produce mechanical energy. How does it do that? You burn gasoline. The gasoline creates smoke. The smoke moves a turbine. Mechanical energy. Right? I told you that mechanical is the movement of something. The gasoline is the chemical. You burn it, and it creates smoke and physically turns a turbine. That's transfer of energy, converting chemical energy to mechanical energy. Another one is electrical energy can produce radiant energy. You see that right here. The movement of electrons can then produce something that we can see visually. Then, however, so that's great. You can convert energy, but there's an important concept that you have to understand. Is that you can never, ever convert energy or convert energy types without losing some of them. Okay? This is very important. You will always lose energy when you convert from one type to the next. Meaning that if I burn gasoline and convert it into mechanical energy, there is energy lost. And how is it being lost? It's always lost as heat. It will always be lost as heat. If I burn gasoline, you all understand that it produces a lot of heat. If I go up and touch this light bulb, you understand that it produces a lot of heat. That's energy lost. And it will always be lost. And so you can even come down to the chemical component. If I break this bond, I'm producing heat. That's why muscle contraction produces heat. We are converting energy from one form to the next. That's why it helps us regulate body temperature. Okay? So understand that when we are converting energy, we will lose it as heat. And obviously, this can be very useful, like I just said, body temperature regulation. Okay? See, I can say. Okay. So I've showed you all the model of elements, right? You all have seen, well, actually, you all, let's take, since we did like the quiz and stuff, let's take like a 8-minute break, come back at 10:20, and we'll pick up on this, okay? All right. Taking that time. What? Huh? No. I gotta pick up the pace. The thing is like, we should pass all this for it. We'll finish this one.
Are those clear things that are nailed to the wall
Huh?
in the booths? Are those for you to write on, like a whiteboard
Which ones?
in the hall? Like by the,
I see no.
it's like clear glass, like plastic looking things.
Maybe.
And it's just like where they're sitting, so I assume it's like,
There's a library here. I think it's small.
oh,
Okay. So have I explained to you all that, I've shown you all the orbital model of elements. And you all understand that these electrons are, again, moving around each element in a waveform. Well, in reality, the nucleus is moving too. The protons and the neutrons are moving too. Okay? So every element is moving. Now, these single elements form bonds with other elements, right? And then we make chemicals, or we make molecules. Well, everything's made of molecules. Everything is made of elements over there on the periodic table. So you all have to get an understanding, although you can't see it, that everything is moving in some way, but we can't detect it. Okay? So everything that you see is vibrating in some fashion. Some things are very rigid, and so maybe only the nuclei are just rotating or vibrating just a little bit, but everything's moving. It's undetectable by us, but everything's moving. Within our body, though, we have a lot of stuff going on. Sometimes you can feel stuff moving. This movement, especially in something like a fluid, which is almost entirely our body, causes molecules to collide with one another. Okay? Molecules will bounce off of each other. And when they do, especially if you have molecules that are unstable and looking for stability, they result in interactions. And these interactions are called chemical reactions. Okay? So these things are constantly occurring. Now, the concept of chemical reactions is something that occurs when chemical bonds are formed, rearranged, or broken. That's what a chemical reaction is. And the easiest way to understand is if you have two things, A plus B, and this could be any single molecule you can think of. Anything as large as a huge molecule like DNA, and something else super large, or as tiny as it is two water molecules. Okay? Whatever it is, and it could be A plus B plus C plus D, whatever, etc. Okay? Two things react with each other. These are called reactants or substrates. These are the reacting substances. Come together, and then they form something, whatever it is, it's called a product. It's the result of the reaction. Now, this brings into another concept that we talked about yesterday called the mole. Okay? The mole is how we count how many substances we're adding. So, if, for example, you see a chemical reaction, I don't even think I have any written down because it's not even important to know, like certain chemical reactions. But it is important to understand the concept. Okay? I could put 1A here, or 2A here, or 2B here. It says that I put 2 moles of that substance into the reaction, or I put 3 moles, or whatever it is, and it made 1 mole of AB. Okay, but the way that we add these things are in the form of moles. Okay. And so there are different types of reactions. Just like the chemical bonds, they're all the same thing. It's still the magnets attracting to each other. There's just different reasons and different ways we can have chemical reactions. It's the same thing. A plus B equals AB. And again, there's a lot of variation to this. Okay, they could be super large molecules, it could be super small molecules, there could be 20 molecules here, and there could be 20 molecules on this side, but the overlying concept is you take 2 things and you turn them into one. Or you could do this the opposite way, and we'll talk about that. But there are different reasons and ways that these reactions can occur. Okay, and there's 2 big broad categories. There's one called anabolic, where we're adding smaller molecules together to make something larger. And then there's catabolic, where we have one large molecule and we're breaking them down into smaller things. It is the 2 broad categories, overarching categories. And then there's 4 types that you need to know of chemical bonds. Okay? First one is called synthesis reaction. It's pretty simple to understand. It's also called culmination reaction. This is considered anabolic. And this will always result in a bond formation. Always. So this is the typical A plus B equals AB. Now something we'll learn is that the primary example of this is amino acids making a protein. Now, you'll certainly learn this next exam. I don't necessarily want you all to know these off memory. It would be nice if you know these off memory, but that's okay. On an exam, I'll probably say if you have amino acids that are small molecules and are coming together to form a larger molecule of protein, you would have to tell me that that is a synthesis or a combination reaction, okay? Or anabolic. Okay, next one's called decomposition or reverse synthesis. This is where, again, you're taking larger components and you're breaking them down into smaller ones. This is a catabolic reaction, and this, again, this AB becomes A plus B. Okay, the two small components. Primary example of this is glycogen. You all remember I told you that insulin is there to pull glucose molecules out of the blood and put it into fat tissue. Well, the way that it's stored is that glucose will then bind up to these huge branching molecules called glycogen. So that's where it's stored. And then when we need it, we break these bonds and release it back into the blood. But the building up of glucose molecules to glycogen is breaking down of glycogen to glucose is a decomposition reaction or a reverse synthesis reaction. Now, you could go in the opposite direction, and that would be what type? A synthesis reaction. Synthesis, yeah. And then there's something called exchange displacement reactions. And this is a little bit, I mean, it's not necessarily complicated to understand, but the processes that they go through is a little bit hard to understand, but we'll certainly talk about this later on. But this is where you're breaking a bond and you're forming a new one at the same time, okay? And then I've certainly mentioned this molecule to you, ATP. This is a general structure of it. And you have these 3 phosphate bonds here. And what happens when we use ATP, this is our energy. And we have this potential energy stored here in this chemical bond. To release the energy, we break this bond. And then we have to add it to something else, okay? This is what's occurring whenever we're using energy. We break the bond and we add it to something else. So in an exchange or displacement reaction, we are breaking a bond and we're creating one at the same time. In this case, this is not important. I don't want you to know the specifics of this. We'll talk about this in detail later on. This is actually the process of how we're pulling glucose out of the blood. You have to add a phosphate to glucose to then pull it into the fat tissue. You don't have to know this example, it just makes it easier to understand with this here. So if you want to read that, that's up to you. There's something called redox reactions. Okay? And redox reactions are occurring when we're transferring electrons from one element to the next, or one molecule to the next. So the electron donor, the one that's donated the electron, after it's donated it, becomes what's called oxidized. Okay? The element that's receiving the electron becomes reduced. Now, at the same time, you can say that losing hydrogens result in oxidation, and gaining hydrogens results in a reduction. Okay? Now, this, I certainly had a lot of trouble understanding this concept. And the easiest way that I can tell you to understand this is simply by memorizing losing electrons is oxidation and gaining electrons is reduction. This is just, I mean, it's not an easy way to explain what's called redox reactions. It's simply memorizing it, okay? Now, those are the 4 types of reactions. I want you to know these 4 types of reactions, not necessarily something difficult to memorize because they're sort of in the name: decomposition, synthesis, exchange displacement reactions. So know this, redox reactions, understand these. memorize these. And then we'll talk a little bit about energy required to form a chemical reaction. Okay. So, there's this concept, it's not really a concept, it's just reality, is that chemical reactions require energy or they release energy. Okay? They can only do one of the two. They either require energy or they can release energy. And this is explained by what's called free energy. So free energy is the measure of useful energy either consumed during the process or exerted during the chemical process. So either consumed or exerted during the chemical process. This is what free energy is. Okay. Now, some reactions release a lot of free energy, which gives them the term exergonic. Some reactions need to consume energy, which is called endergonic. Memorize those terms. Now, coming back to here, I mentioned to you that ATP is used to create energy. Well, the breaking of that bond is still a reaction. That would be considered exergonic because we're releasing tons of energy. Now, the building up of something like this might take a lot of energy. It might take energy to build up something like this. So that would be considered endergonic. But there's this diagram that's given, and if you've taken a science class, you've probably seen it before. This is something I really want you to understand, is that on an x-axis, we have reaction progress. So that's why I put A plus B equals, or goes to AB here. This is the progression of the reaction, essentially time. You can put seconds here. The reaction progress. And here on the y-axis is the energy required during each portion of this process. Okay? And this line is the reaction in time. There are some portions that require energy, there's some portions that release energy. Okay? Now, here you can see again, reactants, so I have it lined up, and then products. You're trying to get from here to here. Now, you have to get over this energy requirement. All these reactions need energy. Okay? They need a little bit. Now, when I say that some release a lot, I mean that they're releasing more than they've used to cause the reaction to occur. They all need a little bit of energy to go. That energy that's required is called the energy of activation. This is activation energy. And that's what this hump is. You have to have enough energy, essentially, to get over the hump. And that's what activation energy is. Now, the reasons for that, I don't necessarily want you to understand. Okay? But just know that you have to have a little bit of energy to get over the hump. Now, these graphs will look different depending on if you're releasing energy or you're not, or you're using up energy. Okay? So this is the same graph that's here. This is sort of the general understanding. This is not an endergonic or an exergonic reaction, but they change depending on if they're endergonic or exergonic. So again, understand this is still reactants and this is still products. We're trying to get from here to here. Again, here to here. Now with endergonic reactions, we need energy for it to occur. We're not really releasing any energy. So we have a very high hump to get over. This is still the energy of activation. We require a huge hump to get over. With reactants, with exergonic reactions, you don't need as much energy to get over the hump, and in fact, you start releasing a lot more energy. Now, free energy is also called Gibbs free energy. Okay? And these are interchangeable terms. It was discovered by this guy named, I don't know what his first name is, but he had the name Gibbs. And he discovered this idea of free energy, and so we call it Gibbs free energy. Now, with endergonic reactions, Gibbs free energy will be greater than zero. Endergonic reactions, I need energy for it to occur. Okay? And if you have a Gibbs free energy greater than 0, this is called a non-spontaneous reaction. In essence, the reaction will not occur on its own. This has to be put to memory, because this explains how everything is occurring. All of these reactions that we're saying that are occurring between the elements, they're occurring based on if they're requiring energy or if they're not requiring energy. If it's spontaneous or non-spontaneous. Okay? Now, in this case, exergonic reactions are releasing lots of energy. And in that case, they have a delta G, which is the change in Gibbs free energy. That's how what Gibbs free energy is delta G, of less than 0. Okay? And this states that the reaction is spontaneous. And if it's spontaneous, it will occur on its own. So if I had this molecule and this molecule come together, they will occur on its own without having to require any energy. They'll start breaking and forming whatever bond they need for the reaction to occur. Now, a single reaction typically is just like one bond breaking and forming. Okay? So this occurs for almost every single bond breaking and making. And these molecules are extremely extravagant. So this is occurring a lot. Now, this is just to get you to understand, if we require energy, if we require lots of energy to get over here to the products, it's endergonic. Delta G is greater than 0, so it's non-spontaneous. It will not occur on its own. And again, delta G less than 0 is a spontaneous reaction and will occur on its own. It will occur on its own. Now, that begs the question of if this begs the question of if a reaction occurs on its own, what determines what way it will move? Okay, so in essence, if I say, for example, now this doesn't occur for all molecules. Okay, if I say this one adds to this one spontaneously, you'll understand that this will add to this one without any energy being added to the system. Well, most of the time, spontaneous reactions will also go back this way without any energy being added. Does everybody understand this concept? So, oftentimes, a spontaneous reaction will move this way, and it can also move that way spontaneously. So, how do you determine which way the reaction will go? So if it moves this way without any energy and it moves back this way without any energy, it begs the question, what determines the way that the reaction will go? And this leads to something called Le Chatelier's principle, and it's right here. These reactions are said to be reversible. Now, not all of them, okay? But a reversible reaction, especially a spontaneous reversible reaction, you have to determine which way the reaction will go. And Le Chatelier's principle says that and you will have to know this, says that a reaction will proceed to where the reactants will equal the products. Okay? So, if I have, say, this is my products, okay? And this is my reactants. This is a lot bigger than this, right? Everybody sees this is probably a lot less than this in terms of weight, okay? Imagine that this is the reactants and this is the products. I have more of this than this. What Le Chatelier's principle is saying that I will empty this water, or I will switch the weight to where both of them become equal. Now, once it becomes equal, it's said to be at equilibrium. They're equal. So now the reaction won't proceed either way. The reaction will move in the way to where they become equal. So if this side's heavier than this side, it will shift to where this side will become equal weight to this. Now, what happens if I start making more of this? Then this one becomes heavier, and then it will shift the other one. So it's determined by the concentration or the amount of stuff you have on either side. So if I have more of C and D than I do of A and B, which way will the reaction occur? to the reactants. If I have more of this than I do of this, it will go that way. And if I have more of this than I have of this, then it will move that way. And that's what these arrows are indicating. It's indicating that this reaction will go either way without any energy being added. The energy is the concentration of the products of the reactants. Okay? And if they become equal, when they go to equilibrium, then then it stops. Now, this concept's important because for many reactions that we'll talk about, for many things, like for example glucose, or like for example ATP, there are multiple ways to make the same product. And so sometimes you have multiple things that are making the same product, you don't need as much of that. And so then you start making the reactants. And then maybe you make some of the reactants, and then naturally you just start making the product. Okay, so this is another kind of homeostatic mechanism. Not really homeostasis, but it is kind of like homeostasis. You want to be at equilibrium. And so simply by increasing the amount of substrate or reactant, or increasing the amount of products, you can shift the reaction. Okay? And that's the Chatelier's principle. Now, there are some reactions that are irreversible, and typically these are the ones that require energy. Okay? And so when you see an arrow like this means that the reaction will only occur that way. For the most part. Now, you can go back. I don't want you all to get confused that you can go back, even in an irreversible reaction, but it just requires a little bit more energy. Okay? So, instead of having like this straight arrow this way, sometimes people will draw a very small arrow, and you'll see it in lab, a small arrow going back that way. Because it's not like you can't take this and go back there. It just requires a lot of energy to go back. A lot more than it took to go this way. Again, the path of least resistance. It takes less energy to move this way than it would to go that way. And that's what non-spontaneous reactions are, or irreversible reactions. You can still go in the opposite direction. Okay. And there's this concept, still on par with reactions, is you can have these things called catalysts. Oftentimes these are called enzymes. And there's many different types. Many types of enzymes. Sometimes they're drugs too. And what happens with enzymes is that instead of the energy of activation being this high, if you add an enzyme to the reaction, it will lower the energy required to get to the other side. So it makes it easier for a reaction to occur. And oftentimes, spontaneous reactions have these enzymes, and we have all kinds within our body to help these reactions move to one side to the next. Okay? All it does is lower the energy of activation, allowing the reaction to occur quicker. And honestly, without enzymes, we certainly would not be able to survive. Because this energy of activation would take a lot of time for things to occur. And in this case, I'm giving you an example of how we're taking carbon dioxide into our body and using it, essentially. We don't really use it, but we convert it to other compounds, CO2, to help us release it into the atmosphere. Well, that requires a lot of energy. We require an enzyme for this to occur. If we didn't have the enzyme, then we wouldn't be able to do this reaction as fast. So we really wouldn't be able to survive. Now, catalysts are just one way that you can influence the rate of reactions. There's 3 other ways. This is not the last time you'll see this because these apply to other concepts too, but the first one's temperature. So I have to have these memorized. Higher temperatures will speed up the rate of reaction. If I add heat to the system, then the reaction will go faster. Another one's concentration. If I have a higher concentration of something, it increases the chances of molecules colliding with one another. The chances of molecules colliding with one another, and therefore it increases the rate of reaction. Particle size. This one gets a lot of people. The smaller molecules will increase the rate of the reaction. The reason is that smaller molecules move faster, And so we increase the chances of molecules colliding together to form a chemical reaction. The same with temperature, I didn't mention that, but higher temperatures cause molecules to move faster. And when I'm saying moving, I could be saying moving in the fluid, or I could say the vibration of them, okay? But these chemical reactions will only occur if you have two molecules that collide with one another, okay? So these factors you need to know are increasing rates of reaction. Higher temperature, higher concentration, lower temperature, or lower size, smaller particle size. You know, I think it's really important that we talk about water. You know, water, I don't know if that's okay. All right, well, we will do this later. Probably pick this up back on Monday. So what we'll do for today, you all understand that you have an exam tomorrow, so everything up to this point. We'll do, so we have lab after this. We'll do a study session tonight for the exam. On Zoom. Would people, does anybody have like a preferred time for a study session? Okay, let's do, let's do 7:30. Okay, I'll send you all a Zoom link for 7:30. Come to the Zoom session, but come with questions. Okay, I don't, I try to explain these things in such a way, instead of memorizing, I try to explain the concepts to you all. And if you all don't understand concepts, okay, ask and we can explain them a different way. But this exam is really about understanding concepts. It's not really about memorization. If you understand the concept, it would only make sense that you knew some of these terms, okay? And that's really the way that I try to teach this class. And that's the way that I memorized it, okay? I wasn't, necessarily the top student in my class for a long time, but it wasn't until I started explaining these things to myself, in my bedroom, and in the library, and to friends, that whenever I explain concepts, I realized, oh, I don't know, the term concentration. But if I'm trying to explain this concept, it would only make sense that I knew this term. So it wasn't necessarily memorizing, it was just understanding, and then everything else fell into place. So I want you to understand the video assignment, or do the video assignments, and come to the study session with questions, okay? Because there's not just one way to understand these things. All right, the exam will probably be, I would say, expect about 60 questions, multiple choice. There'll be some matching, and true, false, of course, I'll put those in there. And we'll do one short answer. And when I say short answer, I'm about the sentence. Okay. 60. We'll do a Zoom session tonight, 7:30, but I come here in the mornings, I'll be in this room for you all at about 7:45. So you all can come in and we can do review before class 2. Don't use that as your opportunity to cram, okay? Come, have questions tonight, and study hard. Now we have a quiz in lab today. Hopefully you all are prepared. I think it's a 5-question quiz. And you'll be fine. If you haven't done the syllabus quiz too for this class. Do that. That's the attendance quiz. That's how I show attendance. Does anybody have any other questions? Any questions, period?
Is that hard every week for videos?
Yeah, the video's on it, but just because the exams are here. So,
You said that you were gonna make like a quiz. Right up my interest. Is that just gonna be like this? Is it gonna just be like every exam? Like
Maybe
help with
these.
the exam.
huh?
Like to help with the exam.
I could add a few more questions on here to help with the exam, but it wouldn't be the same as. Oh, maybe I'll do some questions from my last AP exam. So it won't be the same. I'll ask some questions. So I'll do something. I'll put some of those in. Okay. All right, guys. You guys are good to go. I'll see you all upstairs at 11:30. Oh yeah, bring me your note things. Oh yeah. Did anybody answer any questions I didn't give you a note for? Will you give me my phone?